So again, I'm Garrett Rose, University of Tennessee, and I'm going to talk about a Memristor-based implementation of neuromorphic circuit. I'm actually on the other end of the spectrum relative to some of the other, hardware implementations. We're just beginning a project where we'll be implementing a Memristor-based implementation. One of the architectures you heard about yesterday, the Nita and Dana architecture that Katie Schumann presented. Katie's from Oak Ridge National Laboratory, one of our collaborators. So just a brief overview of my talk. So I guess in a past life, I explored circuits that are related to, Memristor-based neuromorphic systems. I'll talk a little bit about that. I'll provide a very brief overview about what memristors are. I think we've heard about that. Most of you are very much aware of what memristors are, but I'll give my 2 cents. And then there's some ideas that I had in the past. And then we'll talk a little bit about where we're going from here. What is this neuromorphic system that we're exploring? How is it a little bit different from some other approaches? And what we're going to do with memristors in this next implementation. So I think we had some very nice discussions about memristors earlier, so I won't spend too much time here, or at least we hope, right? But anyway, the memristor was proposed in 1971 by Lee and Chua as the 4th fundamental device property. And you can kind of see this representation. It sits there with capacitors, resistors, and inductors. So the memristor is there as well. And the way I think about it is it's just a variable resistor. So you can see these multiple resistance levels that you can get from it. And you can change those resistance levels even though it's a 2-terminal device. So just applying a different electric field across it. So if we apply a large electric field and it's a fairly low frequency, you can see we switch to these lower resistance states. In this case, the example is a bipolar device. So if we apply a negative polarity across it, then we can switch from the low resistance to a high resistance. And of course, if the pulses are very fast, then we're not going to really switch much at all. So these are very interesting, certainly for neuromorphic. Other applications where people have been looking at them are just nanoscale logic, memory, so perhaps a next generation flash. Of course, our interests are in neuromorphic computing. And I will note, so the project that we're beginning is funded by the Air Force. We're working in collaboration with the College of Nanoscale Science and Engineering in Albany, where they're actually fabricating some of these memristor devices. You can actually see it right here. What's really nice about CNSE is they have the IBM 10LPE process in-house. So they kind of act as a fab underneath the umbrella of a university, in a sense. So they're able to integrate their memristors right on top of, you see metal 1 from the 10LPE process, and there's the memristor right on top of that, and right below the metal 2 stack. So it's all in line with the same process. So we're hoping that gives us some advantages in terms of how we integrate these circuits and some of these interesting systems. And you see the results for this hafnium oxide-based memristor. They've collected a lot of results for different materials, also different materials of the metal. Here, metal 2 is implemented with copper. Apparently, if you implement that with, say, tungsten or aluminum, you get very different properties. Here, you can probably tell that the on-off ratio, for instance, is relatively small. We can increase that playing around with these materials. It was pointed out earlier that variability is, of course, an issue with memristors. And you can see that here, actually. So variability in the resistance states and some of the switching properties. But what we think is nice is that these devices do yield, they're starting to yield better. Even though they're still experimental devices, they're yielding better than they did in the past. I don't have exact numbers. And we're hoping, we do include variability in our models, we're hoping that variability can be dealt with the, inherent fault tolerance of a neuromorphic system. So we're very hopeful for this technology moving forward. So just more background as far as prior work. So this is I called it a programmable threshold gate array, and this is a few years ago. I'm a nanoelectronic circuit designer, is how I think of myself. I think an interesting thing is that I wouldn't even call it neural, I just called it a threshold gate at that time for whatever reason. You can read into that however you like. But this does act a lot like a very basic neural network. Here you have multiple inputs, and the memristors, as I described them, are artificial synapses In this case, we have these, each cross point will have these little current mirrors, so 2 transistors with our memristors. Reflect the current, we'll sum up the current on the column, and in this case, we have a reference current that we're going to use to act as the threshold. So if we're below that reference current, we get a 0. If we're above it, we'll get a 1. So very basic threshold logic array. So in this case, CMOS is used as our neurons. And I snuck these slides in. This is some other work that I had done in the past. I'll tell you why I snuck it in, but we also looked at these resonant tunneling diodes. At the time, well, you go back about 10 years ago or so, people were looking into molecular electronics. So we had actually switches that behaved a lot like these metal oxide memristors, but they were built with molecular materials. Another device that people were playing around with based on molecular electronics were resonant tunneling diodes. So I thought, oh, well, now we can kind of resurrect this old idea. This is actually a Godot pair. It was originally proposed in 1960. But these are 2-terminal resonant tunneling diodes, and that means that you have a negative differential resistance region in its IV curve. Because of that, if you stack them on top of one another, you get these 3 operating points, 2 of which would be stable. And it behaves basically like a latch using only 2-terminal nanoscale devices. So this device, if we combine that with these memristor switches, we can have essentially a nanoscale neuron along with our nanoscale synapses. So these little boxes, each one would have this circuit inside of it. We're driving that with, in this case, a row of our memristor synapses. So our synapses drive the little simple neuron, and we go on to the next layer and so forth. One thing to note about if it's a diode, this peak to valley current ratio is dictating your threshold essentially. So the diode itself, that might be somewhat fixed. However, there are other devices based on the same property, or essentially resonant tunneling transistor, where we can sort of modulate the size of that peak. So we can modulate the threshold as well. So that might be interesting. So just some results, again, from before. Or again, we have these Godot pair-based or RTD-based latches, and we have our memristors driving it. This is a very simple toy problem where we're trying to recognize just rectangles versus triangles. So simple images, and you can see the weights, effective weights for this. And then the result, if it's a good rectangle, it'll give us a 1. A triangle will give us a 0. And even if there's some noise, we still recognize a rectangle versus a triangle. It's very simple. But the thing to note is that power is very low. I mean, this is just looking at this nanoscale piece. We're not considering all of the interface circuitry, which of course we would need. But if we just consider all the nano stuff, pretty low. And in this case, this was 2012. We were looking at the Hewlett-Packard memristors. That's what we were modeling. So for those devices, we got pretty good performance in terms of delay as well. So low power, pretty energy efficient circuits. So of course, even if we're just using this as a programmable gate array, we're not even ready to call it a neural network just yet, we still need to configure it somehow. So in this, I guess, moving toward a more neural approach, we did think about training, and that's basically what you see here, where we have something of a stochastic gradient descent implemented using a circuit. These circuits, what's inside the boxes, were implemented all with CMOS. And this is all in simulation, though. The local trainers, they would just be, they could be a transistor. It's just selecting the device, maybe a pass gate or something. But we do have to have some transistor or something that will individually select our memristor synapses, because we'll train them a little bit differently in this model. For this particular example, you see we're showing an expectation. We want to train. This is the actual output that we get. And this is supervised learning. So after several cycles, we'll eventually train it so it behaves the way we want it to. The neat thing that we're showing here is that with this global local training approach, the memristors do evolve, they'll change. In this case, one memristor finds its place earlier than the others. These keep on, and then they hit a point where everything sort of matches. And that's very similar to what I'll describe later, so I'll kind of leave it to that at that point. Okay, so now I just want to talk about our current work, where we're going with our collaborations with Oak Ridge National Laboratory as well as the Air Force. And I'll start by just giving a brief review of what you heard about yesterday from Dr. Schumann. Katie Schumann, as I mentioned, she developed this neuro-inspired dynamic architecture, or neuromorphic architecture. She's now at Oak Ridge National Laboratory, still working on this. And there are a few things to point out about this architecture. You can kind of see, basically the way it works. You're going to accumulate charge through these, weighted synapses. And once the accumulated charge in the neuron hits some threshold, you'll have a firing event. And then, of course, you go to the next stage where things will accumulate again. The network itself, as she showed you, was represented in 3D space. I think of that as somewhat of a 3D delay space, because the synapses, the distance between synapses in this architecture represent their respective delays. So the synapses have not only weights, but they also have a delay along with them. The neurons also have two parameters. Of course, a threshold, but they also have a refractory period, and all of these are configurable. This is somewhat a simple neuromorphic model in that there's just two parameters per element, but one is sort of in the time dimension, and one we can think of as being more of a spatial dimension per these elements. And so we hope that that gives us enough that we can do some interesting things for spatiotemporal data, as well as some of the other classification problems. Another thing to point out is that with Nita, the way Katie has explored this, and the way we're continuing to explore this, is we start with evolutionary optimization. So the networks are configured here through evolutionary optimization. So you determine the optimal structure as well as the initial parameters, the weights, the thresholds, the delays, and so on. So the structure itself is optimized. It's not fixed, all offline, and then we allow some online learning to, adapt in time. So we do have an implementation of this, a digital representation that we've implemented using FPGAs. That's the Dana, or Dynamic Adaptive Neural Network Array. This was developed by my colleague, Mark Dean, at the University of Tennessee. And it's an array of programmable neural network elements. And you can the way I think of it is sort of a neuromorphic FPGA. So we can configure these various blocks to act as neurons or synapses. The synapses, really, a lot of that's going to be configuring the delay. That's what's taking up most of the area there. Each element, whether it be a synapse or a neuron, can connect to up to 16 of its neighbors. So you can see the illustrations here where there's 16 possible connections, and you connect those in a way not too different than in an FPGA. So again, we use evolutionary optimization online along with a simulator that we've developed in-house to represent this Dana architecture, Dana system, in order to optimize the structure that we're going to put onto the Dana, as well as to initialize the weights and the thresholds and the delays that we're using. And just some results. Again, this is just one of several results that Katie had showed yesterday. And I don't wanted to put this here just because even though we have a simple architecture, two parameters per neuron, 2 parameters per synapse, we do pretty well, at least for these classification problems, relative to a lot of other different approaches. So you can kind of see this is the classification error for the iris data set, and down here you see the results for Nita and Dana. So pretty low error related to a lot of these other things. So we're very hopeful, again, that we can do a lot, even though we have a pretty simple model to start with. In fact, that's something that we want, especially from a nano perspective. That simplicity is something I think is necessary, because we would like to have very compact, low-energy circuits that we implement these things with. So moving toward a Memristor implementation of Dana, or more generally a Memristor implementation of Nita. We call it Mr. Dana. There are several features that we want to maintain from the Nita Dana architecture. I'll return to this thought later, but one thing to note is we consider implementing these architectures with things like Memristors. The algorithms do we have to have some give. The algorithms have to be adapted a bit, and there's some back and forth. But there are certain features that we do want to maintain. So the structure and the weights, just like with the Dana system, the neuromorphic FPGA, if you will, would be optimized or initialized offline. We would need a way to upload those onto our Memristor implementation of that. I mentioned dynamic adaptation. So we have a depression and potentiation mechanism that we've implemented using these Memristor-based circuits. So I'll show you an example of that in a minute. So we'll maintain that as well to kind of keep the same mechanism we have in Nita and Dana. And like I mentioned earlier, simple neuron and synapse design. So two parameters for our neurons, two parameters for synapses, so programmable thresholds, programmable delays, programmable refractory period for the neuron, programmable weights for the synapses. And of course, these weights would evolve online via the LTP and LTD. And of course, we're leveraging metal oxide memristors for our synapses in particular. We have thought about using them for other parts of the circuit as well. There is a lot of memory, say, for the thresholds. We can use memristor-based memory for that, but we haven't done that quite yet. But mainly, definitely the synapses would be memristors, and this gives us certainly high density and hopefully low power operation based on our prior observations. So the goal is just a memristor-based neuromorphic system that's reconfigurable structure, initialized offline, but has that dynamic adaptability so that it improves itself once everything is configured. Okay, so this looks somewhat crude, but this is just a pretty standard integrator circuit and a comparator implementing the neuron for our Memristor-Dana. There are lots of different ways we can implement this. This is one way we've been working with. Along with it, you see on this side would be our, representing several Memristor-based synapses driving this circuit. And I think what's important to show here is there's, at the end of the neuron, this would be, think of it as a postsynaptic neuron. There's a little feedback loop, which allows us to implement that depression and potentiation. So when the neuron fires, it's not only firing to its output synapses, but also firing back to the input synapses. And then that would be used to potentially potentiate or depress these particular synapses. I should note that the memristors, resistance is it's not a negative, well, except for the NDR devices I showed earlier. You don't typically get negative resistance. But we do want some negative weights in this model. So the way we do that is we have pairs of memristors for our various synapses. One is going to drive a positive current. So if this resistor happens to be smaller than the memristor below it, then we'll drive a net positive current on its output. If this memristor is smaller than the one above it, it'll drive a net negative current, basically pulls current through it. So we think of that as essentially a negative conductance. So the effective conductance here is what we're getting as our weight in this particular model. And that's not too different than other things that we've looked at, or that I've looked at in the past. Helen Lee and Yuren Chen were here. Actually, Miao Hu was here as well. And there's another algorithm we worked on called brain state in a box, where we have pairs of, I guess you could call it twin crossbars, one representing the negative component and the other being the positive component of the weights. And this is essentially what we're doing here. You notice the orientation of these memristors are different. So there's a little line there that's actually on purpose because what happens is that when I fire, so the output postsynaptic neuron fires, on that firing event, I'll get that little pulse on this side of the synapse. And then I should have the negative part of my spike, if you will, on the left side of that synapse. And that's what the effective voltage drop across these memristors will cause the overall weight to potentiate or depress, if that's what it needs to do. But one of these devices has to increase in its resistance and the other decreases. So that's assuming a bipolar operation. So that's how we implement that, is by reversing the polarity of the device itself, so that when we get a positive voltage here, we're going to have effectively a negative voltage across that one. And we can see an example of this potentiation and depression. It might be kind of hard to read. I should have had a schematic to go with it. We'll assume we have two synapses driving a simple neuron. These would be the inputs. So we see a train of very simple little pulses. Those are our spikes. So I should note these are we're just representing these as essentially half VDD, so it's going up to 450 millivolts in this case. And the neuron has a very low threshold. As soon as it gets one spike, it's going to fire. And you can see that down here with V out, where it fires. So V in, this first input fires first. That's enough to cause the output to fire. And since that caused the output firing event, then we'll see that this is the input. The red weight down here is its corresponding weight. It increases its conductance, or meaning it increases its weight, so it potentiates. This output firing event is also simultaneous to this input spike. So the way we have this model implemented is that when this input is simultaneous with the firing event, then we'll depress that one. So we see a decrease in its weight. So we implement that. And of course, this is an example of integrate and fire neurons. So even though we're just showing one, one cycle, if you will, this would, in that integrator, we would just be able to integrate and accumulate charge over time until we reach that threshold. So it's a little different than some of the more basic Memristor-based circuits I showed earlier. So it shouldn't have too much longer. So we're in the initial stages of this, a very basic, proof of concept that to help us optimize the circuits themselves according to the models that we get, or the models and the data we get from Albany. So this is a very basic classification problem where, kind of like the one I showed earlier with the rectangle versus triangle, here we have 4 very simple images. The pixels are just 1-bit pixels, if you will. You can think of 1 as being black, 0 as white. We have a triangle, square, diamond, plus, and we come up with a very simple weight matrix, if you will. And we kind of tailor this. It's not deep learning. It's just a toy problem to optimize the circuit design of the elements themselves. One thing that you do notice, and it's very fuzzy, I apologize for that, but we have the weights slash, and then on the right side of that slash would be the delays. So we are implementing the delays in those synapses. So there is a temporal component even in this toy problem. So you can see the little spikes for representing a triangle. This particular circuit should fire if it recognizes a triangle, and indeed it does. And then you can see the data for showing it a lot of triangles and other shapes. So we get very good accuracy, of course, when there's no noise. When we add a little bit of noise, we're still well above 80% accuracy for the simulation on this toy problem, essentially. Okay, so moving forward, as I mentioned, we want to better understand the constraints for memristor circuits, specifically the memristor circuits based on the devices we're working with, the hafnium oxide devices from Albany. And as we understand that, this should guide any needed algorithmic refinement. And we've seen this a little bit as we go to the Dana implementation of the Nita architecture. So the Nita architecture is, we think of it as purely analog in a sense. We go to Dana, and everything is essentially digital. We're implementing this in an FPGA. So that constrains the way we implement the algorithm. We would like to refine the algorithmic view because we will build simulators. So it's another future work, because there's all this stuff around these systems that we have to think about. That's something that I've enjoyed seeing from a lot of the, a lot of the results presented from more mature projects is that they're showing that, well, yeah, there's the the neuromorphic system, I apologize, but there's also everything around it. You have to actually talk to it. And so we've started to do a lot of that with the FPGA-based systems. We have these interfaces, both hardware, as well as we call it a commander, and there's some other software tools that will interface with the Dana system itself and load a network, load data, retrieve data. There's also the evolutionary optimization software which we've been developing. We just need to tailor this moving forward for the Memristor Dana, for Mr. Dana. And of course, I mentioned there's evolutionary optimization. We think of that as kind of this offline network initialization. But there is some online training or online learning. So moving forward, I'd like to explore this better. What's the balance between how much do we need to initialize? Can we simplify that, especially since we're programming memristors? That may not be trivial. but how can we simplify the offline part of this and maybe utilize online training a little bit and strike a balance between these two things? So it's certainly good and bad. And I will say the far-term consideration, I mentioned these nanoscale RTDs, maybe just tickle your interest, I suppose. I will note that I have a colleague, so that go-to-pair was proposed in 1960, just after the Esaki diode was published, I think in the late 50s actually. And then in the 80s, people were looking at 3.5 implementations of RTDs. As I mentioned, 10, 15 years ago, people were looking at molecular electronic implementations of RTDs. So it's a device that people have been chasing periodically for decades now. We'll recently have a colleague who's working on graphene implementations of resonant tunneling devices. So I'm kind of interested to see if we can get a full nanoscale implementation of these particular systems. So that's just a quick summary. I've kind of hit on all these points, so I won't go through that. But I do want to acknowledge my collaborators. There are a lot of other collaborators. Some of you are here at this workshop, but these are collaborators working on both a project with the Air Force Research Laboratory to implement the hardware, but we're also working with Oak Ridge National Laboratory to explore deep learning configurations on these types of systems. And you can see Thomas Potok, Katie Schumann are here in the audience. Mark Dean and Jim Plank are working closely with me at UTK. And of course, Nate Cady at CNSE is going to help us fabricate. And of course, here are the students working on our project and our sponsors. So thank you for your time. Thank you for staying to the end. It's been a pleasure.
Okay, thank you, Garrett. Are there questions to this final talk? Is that a question, or are you leaving?
Okay.
It's a question, great.
Thank you for a very educational talk. I actually have a very general question, which is, if you want to use memristors as synaptic elements, it seems like the ultimate dream would be a true cross point where you somehow had one resistor at every point. But whenever I see these presented, at least, there's always a lot of overhead. Like you showed the RTDs, you showed this other circuit, I think in the beginning, the current mirror. I guess my question is that dream ever really attainable, or what is the minimum amount of overhead you would need to realize a very dense synaptic array?
I think for neuromorphic, we can do it in crossbars. So that's part of the question. Can we do just resistive crossbars versus having 1T, 1R, or I showed you a 2T, 1R type orientation. Because here we're potentially driving all of the rows with something, or pulling all the columns in that crossbar. Everything's driven in some sense. So that minimizes sneak path currents. And that's your issue with resistive crossbars. So for a neuromorphic or logic implementations in general, crossbars are possible. And there are ways we can configure those. We can have half voltages in all the unselected columns and rows, and then have a higher voltage on the things we're programming. So that's certainly possible. And so that it's feasible. And I briefly mentioned the brain. I didn't talk about it at all here, but brain state in a box is something I worked on in the past. And there we had twin crossbars. Those were just resistive crossbar arrays, one being for the, negative component, the other being the positive component. And everything was driven on the periphery. So the cross points were just resistive. So I think it's certainly feasible. But having transistors in there do give you some advantages. So.
Thank you.
Thank you.
Other questions? If that's not the case, then let's thank Garrett again.
Thank you.